I just want to give you a quick rundown through the history of these metals. They were not invented yesterday. They've been around for many, many years. First observation of these metals, of these shape memory alloys, was observed in gold cadmium alloys back in 1932. And there were some advances on the art as far as looking at the fundamental science, not really devices or components made out of these materials, but they were most of us in scientific nature of things, looking at what's happening in the microstructure or what's happening in the mechanical response, but nothing designed with yet. So in 1937, there are a couple of different things in between years here, so I'm just highlighting the key, some of the key aspects of these materials here. And later on, as I describe what shape memory alloys, you'll probably relate back to these authors that started it all back in the days. So you can see here that back in 1949, and the reason I choose different countries is to show you that the whole world was looking into these things back in the 1940s. These authors here, these days we call shape memory alloys, a lot of people call them thermoelastics. Turns out that in 1949, that was the first time a word thermoelastic was used, and I will describe that to you as we dive into it. Then in 1951, there was the very first observation of this nature of these curves here. These curves, you've probably seen them in the past. They called hysteresis curves, basically a load or some sort of response as a function of temperature. And that's what's used to describe shape memory alloys in the first place. So that was the very first observation or test conducted to show that you can get this dimensional changes as you heat and cool. You get this envelope, this dimensional changes in a gold cadmium alloy, also using resistivity. But then there was a major change here in the late 50s, early 60s. So here's a picture of a gentleman by the name of William Buehler. He was working at a naval ordnance lab, and he was tasked with working on a lot of intermetallics, not shape memory alloys in specific. He made a number of different alloys, number of different combinations. One of those combinations was nickel and titanium mixture, created the very first what we call nickel titanium alloy, or also known as nitinol for Nickel Titanium Naval Ordnance Laboratory. And that was done by Buehler. In fact, if you read some of his biographies and things, he describes it. People say that it was an accident that this happened back in the days. And he described it as not really an accident. It was a planned discovery. And I really like that sentence there. He was not planning to work to find shape memory alloys, but his research and work on similar alloys, he stumbled on nickel titanium formulation. And on that, what he did actually, they were back in the days, they were doing sound checks. So they take a piece of bar and hit it with something and it rings, and just happens to ring differently. This nickel and titanium, when they hit it with a rod, that ringing, that it was much different than what the other metals he made. And then that was very curious, and that's how they started working on it, looking into it more and doing more research, more formulations, and that was the birth of nickel titanium shape memory alloys, which are now the basis of probably 98% of everything that is shape memory out there, medical devices or aerospace or whatever that is. So that's just to give you a little. It's good to acknowledge this people that started it all back in the days and put it in perspective. After that, once that happened, then you started to see a lot more applications, not just fundamental studies anymore, like microscopy and whatnot. And now the very, very early studies NASA involved. By the way, right after this discovery by William Buehler, NASA funded 2 studies, one to Goodyear, one to Battelle, to characterize these materials, like 2 or 3 years right after. So NASA was in the thick of shape memory alloys when this thing started. They funded Goodyear and Battelle, and they did, and you can still find those reports out there, and they did all kind of characterization from thermal, mechanical, some of them were magnetic, and all kind of different tests. So after that, there were a number of different applications. From my research, this is the very first space application that I was able to find in the Nimbus spacecraft. It was actually a demonstration of moving these louvers over here that you can see using a shape memory alloy wire. So that was the first space application in 1968, or at least a demonstration. In 1969, a group of people led by Anderson designed these wires here. These wires are shape memory alloys for braces. And that was the very first medical application. And after that, there were tons of different things that came up on the medical field. But this implant using what's known as superelastic alloys, I will describe that in a minute, for orthodontic devices. That was a major breakthrough until today. These are being used. I'm not sure if any of you have braces, you might want to check with your doctor to see if they are shape memory or not. And most likely they will be nickel titanium alloy. And then after that, there were a number of different applications. One of them is this one for space. In 1970 was the first recorded aeronautics applications, if you will. This is on the aircraft, a coupler that they use that is shape memory alloy to fix pipes on an F-14. So that and goes on 1986 and so on. And then I try to summarize them here for from the beginning again in one chart. You can see there are tons of different applications, demonstrations, flight tests, wind tunnel tests in the aeronautics to today, 2020. And there's also the corresponding things for space, and you name it, all kind of different applications. Some are devices, some are demonstrations on all kind of satellites, devices, probes. In fact, even now in the Mars rovers, I'll show you a picture later, they have shape memory alloys used for some deploying function or some sort of device that they're using in there. So hopefully that gives you a quick rundown when this started back in the 1930s, major discovery in the 1950s by William Bueller in the Naval Ordnance Lab, and from there applications went left and right using, I would say, a majority of it's nickel titanium, but as I will be showing you later, there's all kind of different other formulations that people use or are using. So what is shape memory alloy? What is a shape memory alloy? So look at the name. There is a shape, there is a memory, an alloy. So an alloy here, I'm referring to just a metal, a mixture of different elements that gives you an alloy. But this alloy has a memory. The material can remember multiple states. It can go back and forth from one state to the other just by applying load or temperature or some other stimulus. Now imagine you have ice, cube of ice that goes to water. So that's a phase transformation. You know, it goes from a solid to a liquid. That's a phase transformation. So here shape memory alloys are similar. They go through a phase transformation, but this phase transformation is solid to another kind of solid. There is no melting involved here. Just like if you have imagine you have a cube of ice that goes to a triangular piece of ice without melting, just by applying a load or applying some heat signature or some other means of inducing such transformation. And that's what I'm trying to depict here with this picture. So imagine these atoms are arranged in some fashion, in this cube fashion right here. This is what we call a parent phase. Okay? This is the reference phase or the parent phase. These atoms are arranged in this fashion in the simplified model here. Once you cool it or you deform it, it can go to this rectangular shape in this fashion, or it can go to this shear component here and stretching and so on, or it can go up this way. It doesn't have to go that way, but it could go up this way. So all these different paths, if you will, or the different directions is what enables the memory in shape memory alloys. More so here, when you see this cube, it has a relationship with this form, or with this form, or this one. So the difference between this metal and conventional metal is there is a relationship that allows this block here to go from here and back and forth without breaking any bonds. So there's always a relationship maintained, which gives us the memory, and this memory is triggered by heat, temperature, or triggered by some sort of load. It could be some other ways of magnetic field, lights, or whatever that might be the case. So typically in the high temperature phase, I'll describe one of them. In the high temperature phase, we call the cubic phase, which looks like a cube. If you look at the microstructure, if you look at how the lattice of the structure is arranged, it's going to be cubic. So this cubic phase, also known as the parent phase, and also you will hear me referring to it as the austenite phase. If you've done some literature surveys, or if you encounter some of these materials in papers, it's called the austenite phase. If I cool this austenite phase, or if I deform this austenite phase, it goes to a lower symmetry phase. I'm just going to go to C here, this rectangle looking here. Now the sides are not equal. One is stretched more, and so on. So this side is not equal to this side, is not equal to this side, for example. So this one here is called some papers refer to it as the daughter phase. Why is that? When this one transforms to this cube, to this rectangle is not unique. It can be in this direction, it can be in that direction, it can be in many, many different other directions. So when we call this the parent phase, it can have many children over here. You can see 1 or 2 or up to 12 in some cases, or 6, depending on what that symmetry looks like. And that's important, because one cubic phase, one cubic form or phase can go to many different variants of these lower symmetry phase. And that's what we refer to as the martensite. If you look at martensite, austenite. High temperature phase called austenite is cubic. Low temperature phase called martensite, and it could be some other structure like this rectangle here, which we call orthorhombic, or could be the one, I lost my mouse, just 1 second here, or it could be some sheared block like this, which we call monoclinic, or it could be very much some other kind of different lattice or different structures when you look at the atomic scale. So that's a basic definition of a shape memory alloy. Basically, it's a metal that can change shape, and it remembers both shapes, both directions. It goes from here back to here and so on. Let's look at what gives it that unique property. I was describing elastic and plastic. Just to recap here, in plastic deformation, it's permanent. So there is here's that picture again, just side by side. So in the case of shape memory alloys, it's almost like the elastic version, which is reversible, and the plastic version, which gives you very high displacements or strains. So if you look at this bottom half here, what we call it is inelastic deformation, and it's fully reversible. So now think about this blacks here that I have shown, and I have a little square to show you the parent phase, that austenite phase again. So when you apply heat or you deform it, or you cool it or you deform it, it goes to this sheared kind of geometry. So these planes, they just shear like this zigzag, what we call twinning. The term for it is twinning. But in this process, there is no broken planes like you see here, where you break a plane and it's permanent deformation. This deformation here, enabled by twinning principle, it's reversible. So when I can go from here, load and load, or heat and cool, and so on, I go from this little representation of the cubic austenite phase to this little representation of some other lower symmetry martensite phase. What's the result here? So if you look at that deformation here, if I go just a little bit, it looks like elastic, just like my elastic model over here, straight line. Now, if I go past the elastic region, it goes to what it looks like a plastic deformation right here. The only difference here, if I take this sample and I unload this sample, I remove the load, it comes down like this. But if I stop here and I unload my sample, I take the load out, it actually recovers everything. That's the recovery. So almost like a rubber band, but it's a piece of metal. So this recovery could be in the order of 10 times more than the elastic portion of your conventional metal. So if you conventional metal, aluminum, what have you, you can deform it to 0.6%. 0.6% is what's all reversible. This shape memory alloy here, you can deform it 10 times. That's 6% fully reversible strain. And that's the power of shape memory alloys. So that's keep in mind this principle again. This is reversible, and it goes through enabled via a phase change, a phase transformation from a higher symmetry parent austenite phase to a lower symmetry martensite phase. That's how this happens. Here's a quick picture for you. So again, remember this little twins that you see here. So if we go in a microscope and look at the cold states in the lower symmetry, the martensite phase, what's referred to as the martensite, here are those little ridges that I just showed you. You can see how they're going back and forth. This is actually a real microstructure. It looks like this. This is how it accommodates that deformation. You don't break a plane, they just go into this twin modes that you see here. And now if I take this same metal, same microstructure, and I heat it up, what happens? It goes to the higher symmetry austenite parent phase. And this is the microstructure of the same material. You can see, just like you have your conventional aluminum or steel, what have you, titanium, grains next to grains next to grains. And sometimes it's hard to believe that this is the actual same exact material, just heat and cool between them. It goes from this to this. And as this is done at a microscopic level, but the end result, if you take a components, because this little grain is going to here and the next one is going to here, you have a macroscopic deformation that is reversible, controlled by temperature or load or some other stimulus. So hopefully this gives you a good idea of what shape memory alloy from a microstructure level looks like, what's the terminology used to describe shape memory alloys, the austenite martensite, and why it is reversible. Here is a one version of the shape memory alloy, and I'm going to describe it here. So we start, hopefully you can see my little pen here. I'm at 0. I'm in slide 13. So we start from 0, and this is the austenite phase, and I just told you it's the parent phase and it's the cubic phase. I cool it under 0 stress, 0 load to 1. Nothing happens. It just accommodates this little square that you see into some twin mode that you see here. Nothing happens. No macroscopic changes because those twinning that's occurring is very small. Now I'm going to take my piece of metal and I'm going to deform it. I'm going to go from 1 to 2. If I didn't tell you anything about this material and I unload to 3, it could look like a elastic plastic deformation, like you pull in a piece of steel. Okay, if I don't show you the bottom half here, just the blue curve, load to 2 and load to 3, remove load. So this deformation in the order of 6 or 7% in some alloys is isothermal. It's done at a constant temperature, say let's, for simplicity, let's say room temperature. If I go from 3 and now I heat this material, I apply it to heat. Once I apply heat, this material actually recovers. It goes back to 0. And in the process, as these phases are changing, the phase transformation is occurring. It goes from some sort of low symmetry microstructure to high symmetry. I recover all this deformation, just like the metal never was deformed before. So this mechanical deformation is recovered by this heating part of things. And now you're back to zero. So this cycle is repeatable by load, unload, heat, and cool. You can do it all day in a perfect condition. This process here, and this is important if you're taking notes, hopefully, I have some exercises at the end that we will do together. But just remember, this process, when it's recovered by heat, is known as SME, or the shape memory effect. Okay, shape memory effect, which refers to a temperature-induced transformation. So you have to apply heat for it to recover. It's known as the shape memory effect. Okay. Now, in the shape memory effect, if I take this plot here, this bottom curve, and I kind of just look at the 2D, forget about the 3D plot now. Now let's start at room temperature right here. I'm right here. Now I start heating under a load. Now I take a piece of metal, I apply a load to it, 2, and I don't unload. I stay at 2. So this is fully loaded metal or components, and then I heat. As I heat, I go this way, and then I generate quite a bit of displacement. Okay, where is it going? It's going to the austenite parent phase, and when I cool, again, it follows the same path. Some of you may think that it follows the same path as goes this way. Well, that's one way to do it. Okay, but actually in most shape memory alloys, the path that it takes is this way, and so on. Okay, and I'm exaggerating this to show you what's happening in shape memory alloys. So how does it start first? Let's go back to the red. To the red here, and when we start heating, we reach some critical temperature. Okay, some temperature known as AS. And probably most of you, some of you may be guessing what AS stands for. So when I'm heating, I'm going to the austenite. This AS stands for austenite start. So I start my transformation and I go to AF. You can guess what AF stands for. AF stands for austenite finish. That's when the end of my transformation. So now I keep heating around here, nothing happens. No change in dimension. The strain could be displacement, could be twist, could be elongation, could be shrinking, whatever the component might do. Now when I'm heating, when I'm cooling back up now I'm going to cool my material. I'm here. I'm cooling. You start cooling until you reach a critical temperature. Now, this critical temperature, known as MS, stands for martensite starts. That's where you start the martensite transformation, and you go all the way up here until you finish the transformation, martensite finish, and then you go back to cool, starting temperature. So now a couple of things that you see here. This path here, it doesn't take the same path. This little gap in between is known as the hysteresis. This hysteresis can be anywhere from 10 to 100 degrees C, for example, depending on the alloy. This length here, when it heat, it shrunk by this much, is known as transformation strain, or the actuation that you expect from this material. How much is it going to expand? And then if this material was perfectly stable, when I cool, it actually go back to home, to here. But it doesn't. Most of the time it doesn't. It has a gap known as residual strain. So you have to condition this material to be able to close this gap. So every time you heat and cool, it goes back to home over here. So this is extremely critical in the world of shape memory effect. And if you want to design any actuator with shape memory alloys, this is the curve that you need to look at and understand fully. That's why I'm spending a little bit more time on it. But I have more examples to come, and I'll show you how it goes. This is just in a cartoonish way what it looks like between temperatures. Again, when I'm heating, I go through austenite start and finish. It goes to the austenite phase. And then when I'm cooling, it goes to martensite start and finish, and it goes to that lower symmetry twinned microstructure. Now the second type, so the first type is shape memory effect. I can change the material by applying heat. Not always the same. You can do it also by what's known as superelasticity. Some call it pseudoelasticity. What it is, I refer to it as SE. It stands for superelasticity or pseudoelasticity, and basically it's a stress-induced transformation. How does this happen? Now I'm sitting at 0 here. My microstructure is austenitic, okay, cubic. I start loading this material. At some point, it transforms to starts transforming to martensite, and then finishes the martensite. And then as I reverse the load, it comes back through this path, austenite, and then it finishes the austenites. This is just by pull it and let it go, basically. Load and load. And this is fully reversible, what's known as the shape memory alloy, a shape memory as known as superelasticity. The principle is the same. It's a phase change. It goes from this nice cube to the shear components, and once you unload, it goes back to this cube. So the underlying principle is exactly the same, except that this is triggered by load versus the shape memory effect, or SME, is triggered by temperature. Please, if you have any questions, let me know. There is another, I'm in slide 18 of your package. There's also other ways to move the shape memory alloys depending on the composition. There is magnetic or ferromagnetic shape memory alloys that you can change the microstructure by applying or removing a magnetic field. This could be advantageous where we have a magnet available, or you can guess already that if you have, for example, a shape memory effect, you have to introduce heats and you have to remove heats. So that means time. Magnet, you can turn a magnet on and off much easier, faster. So this means you can choose one or the other depending on the application. If the application requires high frequency, you need to actuate or move something very quickly. Maybe a magnetic shape memory alloy is the way to go. If you can afford a few seconds to heat and cool, or if you don't have a magnet, then you can use the shape memory effect. Or if none of them, if you have a place where you can apply load and remove load, then you use the superelasticity. And just for completeness and awareness, there are also shape memory polymers, the same kind of principle. You can heat them and cool them, but of course also you can introduce light. There are some neat principles of light-induced transformation, heat and cool. And for some very high temperatures, there's also shape memory ceramics. The same exact principle, but they're not metals, they are ceramics. Okay, so that's about shape memory alloys, how they work, what types we have, magnetic, mechanical, polymers, ceramics, and so on. And here I wanted to introduce you how to form a shape. So how do you introduce that memory? So imagine you have a square and you want it to now remember to be a triangle. So you have to form it into a triangle. So that process we call shape setting, okay? Or the good example is if you have a straight wire, but you want it to be formed into a spring. So you want it to be formed into a coil, like a helical spring. How do you do that? In the world of shape memory, we call it simply shape setting. So if I take my metal and I apply some load to it, okay, stretch it, just like this coupon shown here, and then I heat it under a constraint. So I hold it not to move, like in a jig or a platform or something that you have to hold it in place. And then you heat it and cool it. Suddenly the new shape is this long shape. Now, if you look at the microstructure of this shape versus this shape on top, they are identical. The only thing different is the remembered shape. If I want to form this into a U shape like this and repeat this procedure and like constrain it here or something, you know, and then heat it and cool it under a constraint, the new shape is going to be this bow shape or an S shape or whatever it is. But the bottom, my point here is you can always remove the previous memory and put in a new memory into this metal, like program a new one by doing this procedure. And this is a very powerful procedure. And I put in here actually some values in case we'd like to go try it and how to shape set things. But this is how you form the initial shape. And we do that also. Here's an example. For instance, these little springs were a piece of wires. We take little mandrels, cut some threads, wind this wire in there, put the sleeve to hold them in place, throw them in a furnace in the sleeve so they don't spool back out, heat them and cool them under some temperature environments and so on. And finally, you have a new form of that wire. Okay. This wire now, if you apply a load to it, like a helical spring, it will shrink and contract and extend and so on and so forth. This is the simplest form of using shape setting procedure to create a new geometry, whether it's a spring or a beam or a triangle or whatever that is that you're trying to do. Okay, so I just want to go through a few examples here before we start doing some exercises. Comparison, shape memory alloys, particularly the one that are actuated by heat, shape memory effect, they're prime users for actuator. An actuator basically is something that you can use to move or control a system. An example here, electric motor, a hydraulic system, a mechanical rack and pinion, and I put thermal here for SMA. Okay, SMA stands for shape memory alloys. Here is just a quick, real example on, I should say, simplified example of electric motor. You need power, converter, cables, and so on and so forth to build the motor to move something from position A to position B. Here's another schematic of a pneumatic system, a hydraulic system, and these are what's required. And then you can go into a thermal system, which is shape memory alloy, that looks something like this. And what I'm trying to show here is that shape memory alloy actuator can be a very simplified form, can be very lightweight, can be very compact, and do the function that your electric motor or hydraulic motors can do. Now you have to trade it properly. You have to look at the other aspect. One thing is having a lightweight, compact actuator that costs $1 million versus having a hydraulic motor that costs $100. So there's cost weighting in there. There are other things that you need to look at as far as life. Maybe you look at frequencies and so on. But in a general sense, where it makes sense, shape memory alloys are known to be very lightweight and very compact that you can package in tiny places where having a motor like a pneumatic hydraulic, there's no hope of doing that anywhere. So here's what I just described. One thing for especially for us NASA, for space application and things, if you have some sort of deployment mechanism, if you're going to deploy a sail or a panel or a boom or fairings, SMAs are debris-less, right? And spark-free operation. You can apply a signal. There is no sparking. There is no debris, like if you have explosives or some sort of pyro devices to release things. There's no shock from the explosion. So that's a very neat benefit from having shape memory actuators doing such a thing. Silent operation, you don't hear it. In fact, there are some cars in Europe that they replace the mirror. When you adjust your mirror, you push that little button and you hear that zzz going on. Well, some high-end cars, they don't want to hear that. So they replace them with shape memory alloys, which are very silent. Again, is that the right application? I don't know, but it's there. Maybe there are some applications out there that require such operation, and so on and so forth. This is just a few screenshots here to show you again the comparison of power weight ratio as a function of weight. Again, the example, the SMAs are down here. Weight-wise, they are very lightweight, and they can perform kind of like many other actuators in its class over here. Of course, if you go up here where you have hydraulics, you get a lot more power, but of course you get heavy. It gets heavier over here. And this region over here. So that shows you that SMA can be light. SMAs can produce very high power. If you look at another example here from reference 18. You look at the output as a function of weight. And these are sort of other kind of actuators. You can look at the solenoid, thermostat, bimetallic, and so on. You can see SMA straight wires have high outputs over here and lightweights. SMA coil springs can span a range over here depending on how you coil your springs, if you make it stiff or flimsy or what have you. And you can see how it compares to magnetic solenoids and so on. This is also another important thing here to compare to other metals. If you look at the stress limits as a function of recoverable strain, how much deformation you can get back. And here's one that is, where's our SMAs here? You can see here we have a number of different alloys. Here are some shape memory alloys in the middle. High stress limits, they can handle high stresses, they are a piece of metal, but can give you in the order of 6, 7, 8% recoverability. Versus aluminum, if you go past the elastic region, well, it's going to yield, go plastic, and you're not going to be able to use it anymore. There are other kinds of shape memory alloys over here that are promising, and they show some very high recoverability at very high stresses. So why I'm showing you this, that the idea here is I'm showing you this chart to tell you that shape memory alloy metals, they are metal that can withstand stresses. So you can use it as a part of the structure to hold a joint or a hinge or what have you, but at the same time, it can do a function of an actuator. So that's what I'm showing you this plot here. And then you can go into bandwidth comparison. This is important. If you look at the plot here, bandwidth versus strain, you can see that SMAs are slow. They are up here. They can give you high strain, but they are slow in the 1 hertz or so on. Why is that for this particular SMA? Well, you have to heat them and cool them. So it's a heat transfer problem here. You have to heat the metal and somehow you have to remove that heat. And that process could be lengthy. If you have a very tiny wire, SMA wire actuator, that process could be, hundreds of milliseconds. If you have an actuator that is 100 pounds, well, you need to wait for it to cool for a while. So it could be many seconds. So that's one of the not disadvantages, but something to be very much aware on using shape memory alloys for an application that requires speed. For that, you can try to use magnetic shape memory alloys that's shown here. Nickel, manganese, gallium are ferromagnetic shape memory alloys, and they are higher bandwidth. You can switch a magnet on and off very fast versus nitinol, which is shape memory alloy, conventional nickel titanium. It gives you a lot higher specific energy, but at knockdown on frequency. So this is something to keep in mind. So with that, I listed this, by the way, when I was going through the slide, when you see this numbers here, they refer to the original work, so give you a chance to go look at the whole story there and everything. So I summarized them for you here. So what I would like to do next, typically we have an exercise where you can build your own springs and stuff, but because we can't do that, so I prepared this little document here where hopefully we can work together here. Now I really need participation. I really need you to participate here and help me through this exercise. So case 1, these are a few different questions, and I will ask questions, and if you're kind enough, participate and answer the question. So here, case 1. Okay, I have a spring, and I'm gonna load it and unload it. Okay, when I did that, it stretched and it stayed stretched, right? Because I just pulled it and it stayed pulled. Now I heat this spring. It went to, it looks like original shape, and then when I cooled it, it went back to this. It stayed as is. Just the blue and sort of the red to show you the shapes. What SMA principle is this? I'm sorry. Can you repeat it? I didn't hear you.
Shape setting.
Okay. Shape setting is a good guess.
Shape memory effect.
Okay. So I heard, wonderful. So I heard 3 things. I heard shape memory effect. I heard elastic. and I heard shape setting. Okay, so here is the answer. So whoever said shape memory effect is the correct answer. Okay, and here's that curve. I load and I unload, and it stays stretched. If it was elastic, it will go back to this shape, but it did not. So whoever said elastic, shame on you. I'm just kidding. Then I heat, it goes back to 0, right? Back home what it was. And then when I cool it, it stays like this. So the correct answer is shape memory effect. In fact, there's one on top of it. This is called one-way shape memory effect. So meaning if I heat and cool, nothing happens under no load. Just heat and cool, it stays that way. Now let me go to my next slide. Now case 2, and also I need your participation here, please. I take this spring. Sorry, let me go and address one question that someone mentioned, shape setting, and I'm going to tell you why not. Shape setting, if I would do this one, I said load and load, and I would hold it in place. I would constrain it. I didn't constrain it in place. I just heat it in freeform to go back. If it was constrained, that procedure will be called shape setting. So hopefully that helps clarify. Now my second case, I go to this spring again, and I pull my spring and I remove the load, and it stays stretched. And then I heat this. It goes back to the original shape, but then I cool it and it goes back to the deformed shape. What is this called?
Temperature-induced transformation.
Temperature-induced transformation. That is correct. Can you? Okay. It's the shape memory effect, which is the temperature-induced transformation, but there's a layer on top of it. It's called a two-way. The previous one, if I take this spring and I cool it, well, nothing happens to it. Now, if I under no load, under 0 applied load, I heat, it go back to 0. Now I cool, it doesn't go back to 1. Hopefully you can see my pointer. It actually behaves like an actuator here under 0 stress. This phenomena here is called two-way shape memory effect. The difference here is one way, once you heat and cool under 0 stress, nothing happens. But in two-way, as you heat and cool under 0 stress or 0 load, it remembers two states. It remembers the cold state and it remembers the hot state. And this phenomena here is very useful when you have components where you have very little or 0 stress at all. And you want it to remember two states like close a valve, open a valve with no load, or a switch or a breaker or what have you. So remember, this one is very useful. It's called two-way shape memory effect. It's also shape memory effect, but it has two memories versus one, if you will. Good. Let's go to this case here. Okay. Now I'm going to load, but I'm going to keep that load. Okay. I'm not going to remove the load. And then I'm going to heat it and cool it. And then heat and cool. Okay. I didn't go through this here, but the only difference between this one and the previous one is this one is one-way shape memory effect, but the only difference here, I'm biasing it. I'm applying an external load. I never remove the load. Imagine you have a piece of a spring and you put a dead weight on it, hang a dead weight. And then, in fact, that's what I do in the classroom. If you heat and cool that spring, that dead weight is going to go up and down. So there is a load applied to it, an external load. Now in the two-way, there is no external load, but there is an internal load. So the principle is exactly the same. Take a spring, hang a dead weight on it, and heat that spring and cool it. It stretches and then comes out back up. In two-way, imagine I chop off that dead weight and you have nothing hanging, but the spring is still going up and down via two-way. And the only difference here is in the bias mode in slide 33, you have an externally applied force. In slide 32, two-way, you have no externally applied force, but we do something to the metal to make the microstructure inside biased, meaning there is an internal stress to the material that makes it remember two states. So two-way internal state of stress, bias element here, which is, by the way, the most used application on the actuator, is bias shape memory effects. It's one way, but there is an externally applied load. And there are benefits to using one versus the other and when it comes to applications. Okay, let's look at this one here. This one is interesting. Case 3, I load and I unload and I heat, and then nothing happens. It doesn't go back to shape. What kind of shape memory is this? Okay, so we'll go with magnetic, and the answer is no. This is simply plastic deformation. It's not even a shape memory alloy. It's just a metal. You know, that's how metals behave. You know, you pull it past the elastic plastic deformation, you heat it or not, it just went plastic. There's no recovery. So it's just an example to kind of relate it back to what the conventional metals look like. So it's not a magnetic alloy. There's no recovery or anything here, and the heat didn't do anything to it. All right. Or
can I ask you a question?
Yes, you can.
With you talked about the one-way shape memory effect and the two-way. What's the difference? Is it a different material?
No. So this could be the same material when you make a two-way, when you program, if I can use that word, when you train or condition the material to remember a two-way, you have to condition it quite a bit. So you have to apply some thermomechanical profile into the metal to create back stresses, to create stresses internally inside the metal. So in a way, as you heat and cool, there's a stress on the grains that pushes it one way or the other. So that stress is internal to the metal, and you have to do a lot of things to it to get that. Versus one way plus bias. If I had no bias, if I had no applied load, and I'm in slide 33 now, if I have no applied load and I cool, this one is going to stay as is, same length. But because I have an applied load, it's going to force it to stretch again. And when I heat it, it remembers home, and then so on and so forth. But this relies on an external bias, an external force. Does that answer your question?
Yes, thanks.
All right, you're welcome. So back to this example. I take a spring, I load that spring, stretch it like this, and then I unload it, and it goes back to this condition. What do you think this phenomena is, this example is?
Just elastic.
Elastic.
That's just elastic.
Very good. Just pure elastic. And you get your spring back. Now, if I take it one step further, sorry about this image, forget about this image, this is for a different example. If I take this spring and I pull it 10 times more than elastic, and I unload it, and it comes back to the initial shape. What do you think this phenomenon is?
Superelastic.
Superelastic. So this is superelastic example here. So you pull it way past this nice straight line region, which is elastic. You go all the way here, which looks like plastic, but it's not because it's shape memory alloy, and you unload and it goes back to shape. So this is superelastic. Wonderful. Now I'm gonna get a little bit more involved here. So let's look at this case. There's an alloy that I picked. It has an AF, an austenite finish temperature of 100 degrees C. Okay, and I'm going to load it at room temperature. Okay, so now you got to tell me which path, the top or the bottom. I'm going to load it at room temperature. Okay, is it going to stay as is, or are we going to stretch following this curve?
Stay stretched.
Stay stretched. Okay, yes, the answer is it will stay stretched because I'm past the elastic region. So this is not the answer. Now it's stretched. Now I'm going to heat it up. Remember, my AF is 100 C, and I'm going to heat this up to 80 degrees C. What's going to happen to this material, to this springs? Remember, we are on the bottom path here. Now I have two options again. As I heat to 80 degrees C, is it going to go back to original shape, or is it going to be stay stretched? Top or bottom option?
Top.
Top option, okay. Any other guesses? I guess the only other guess will be the bottom. So if you said the top option, if I heat to 80 degrees C, it's going to shrink back to what it was before. And the answer is no. And here's why. Remember, I mentioned that I bought this material, or I made this, its AF is 100 degrees C. Okay, I'm over here. Here's that AF, right? You can see it here. I'm only heating to 80 degrees C. So 80 degrees C is still over here. As I heat here, I didn't do anything. So in order for you to get it to transform, to remember the shape, you have to heat it past this transformation. So you have to go change the shape. This is the dimensional change for it to go. So you have to go past this critical temperature known as the AF. So the path that we have here, you deform it at room temperature, you create a stretch length, and then you heat it to 80 degrees. Actually, nothing happens. It stays like this. If I go heat it to 180 degrees C, like past over here, AF, then yes, it will shrink and go back. So hopefully this what I'm trying to demonstrate here is the importance of these temperatures here, and you should be aware of what they are when you go buy an SMA or use an SMA, because that's what dictates if your actuator is going to move or not move. That's what this temperatures become critical. So now let's look at this example. AF is 0. Now my AF is 0. I have the spring, and I'm going to load it at room temperature. Okay, load and unload. Is it going to go here or here? Top or bottom option?
Top option.
Top option. So I'm going to take the spring, and I'm going to load the spring up, and remove the load is going to go in the top option. And why is that? It's going to go here.
Difference in temperature?
What? Say it again?
The difference in temperature?
Not necessarily, but because it's super elastic. Superelasticity only exists above AF. Only as a strong word, but let's just use it for today's exercises. You have to be above the transformation temperatures, AF. Of 0, I'm loading at a room temperature, which is 25 degrees C, whatever. So I'm above, like you mentioned correctly, I'm above the difference in temperature of AF. My material is super elastic. Now, I take the spring that shrunk back to home, and I heat it to 80 degrees C. What's going to happen? Now we're here, either the top or the bottom option.
Top option.
Top option. And that is correct. So I'm going to do my best to sketch it over here. Hopefully you can see this. So here's my curve, the heating curve. I said my AF is over here, and I'm at room temperature, so I'm pulling over here. I'm deforming over here, so I'm past the transformation. Even if I heat up and I come here, nothing happens. So it stays the same way because I'm done. My transformation is behind me. It's all done. That's what this exercise shows us, that if you are above the AF, you're going to see superelasticity. And if you increase temperature, you don't recover shape because it's already recovered. You don't get any dimensional changes. Okay? All right, let's get more fancy here. There's a match game. So case number 8, my AF is 0 degrees C, okay? And I'm going to take a wire, and I'm going to deform it isothermally constant temperature at the following temperatures. I'm going to do 20. I'm going to heat to 100 degrees C and deform. and I'm going to go to all the way to 300 degrees C and deform it. So now I would just want to help, if you can help me, and I put this line to guide you here with different shapes. Now I would like you to participate and tell me case one, what case is this? Let's start from the bottom left here. What case is this? 1, 2, or 3?
Two.
And I'm not throwing a catch here. These are all shape memory alloys. So this is for real, all shape memory.
Two.
This is 2, okay? What about this one?
1.
This one is 1. And this leaves us with 3. Okay, do we all agree? Is someone there that doesn't agree? Okay. Okay, and so everybody agrees. Wonderful. So
Get
this,
it.
huh?
I don't get it. They're all the load temperatures are above the AF temperature.
Okay, wonderful. Okay, I can explain. I promise you in a minute you will get it. Okay, so but first of all, we all agreed. Some of us agreed that this is the correct answer, and it's wrong. We all wrong. So let me explain why. So now I'm gonna sketch a little bit curve here, and like you mentioned, I'm past the transformation, right? I'm gonna stretch this guy all the way over here. And you can see I like drawing. Typically when I teach this in a classroom, I like to use the board a lot. So let's say this is 1, 2, and 3, right? So this is 20, 100, and 300, okay? So now we're dealing with, this is AF, right? Here is my AF. I'm past the transformation temperature, right? There's my nice curve here. When I told you when I'm past the transformation temperature AF, I'm super elastic, right? So if I take and I pull this sample right here, what do I actually get? I get this one. This is my case 1. Okay, I get a super elastic nature that looks like this and recovery. Now, if I go to higher temperature, this is case 1. This is case 2. If I go to higher temperature, what happens is this plateau, this kind of shape that you see, goes higher. This is my case 2, which is correct. So you see how this plateau is increasing. For example, if I go to slightly higher temperature, this plateau is going to be increasing and increasing. What it means, remember what happens here when I go past this line and I bend? A phase transformation happens. I change my austenite to martensite. As I increase the temperature, I make it a little bit more difficult for that austenite to martensite to transform, which it means I need more load. I need extra load to make that austenite transform to martensite. So I have to apply extra load. Therefore, this one is increasing up. It's going up. Do you see this curve is lower, referring to this dashed line, and this curve have moved? But here's another thing. If I keep heating all the way up there, for those of us that work in material science, the bad stuff happens over here. As you approach higher and higher temperature, this is not too high, 300 C, for example, then your material, like I told you, it requires higher and higher and higher and higher load and keeps going higher. And suddenly, there is the energy for it to transform to martensite is surpassed by your conventional plastic deformation. So the material will rather plastically deform than phase transform. What happens? You get a pair like elastic and plastic deformation, and it looks like your conventional piece of steel or metal. So this condition here has no shape memory properties. The material is a shape memory alloy, but there is no shape memory properties. And this is a very important concept that I will show you an example of so you'll understand it better. Do we have any questions here? Because this is an important concept here.
I thought for condition 3, you had to be at 500 degrees C for that to permanently happen.
No. So you have to be above a temperature that is known as the MD. And the MD, in fact, I have an example that I'm going to go to, so don't steal my thunder just yet. We'll get there. Okay, any other questions?
What was kept constant? What was kept constant, the strain or the applied load?
Let's say strain in this case. Yeah, you go to 3% or 5% strain.
Okay.
Like if you're referring to this, will be like, go to 3% or something like that. For example, they're not drawn to scale, but you can assume that. In that case, that makes our case number 3, and this one is wrong. Okay. And I tried this. Here's that curve here. So initially I gave you this spiel that there's 2 kinds of things. There is shape memory effect and there's superelasticity. And now I'm going to confuse you and tell you they are really the same material. It just depends where you apply it. And that's what I'm trying to demonstrate with this picture here. So imagine my 0C here. My AF, right, is 0C, 0 degrees C. If I go below it, let me try to sketch it here quickly, right? Here's my AF, okay, and it's 0C. If I go below it, if I cool here, I reach this point, which is martensite starts, and then I go change my dimension, and it becomes martensite finish, and then I'm here, I'm fully martensitic, right? What happens when you're fully martensitic? We're down here. When you load and you unload and then you heat, you recover. So this is what I told you, the shape memory effect. You load and load and you can get the shape back by heat. A minute ago, I showed you this schematic here. If I take material and I load here versus here versus here and so on, I get this shape. I get a superelastic curve, nice superelastic curve. If I move higher in temperature, that cubic structure, that austenite structure, needs more energy to convert to martensite. So I need higher load. And I keep heating, higher temperature, I need a much more load to do that. And suddenly, after a critical temperature known as the MD, martensite desist, where now the energy to phase transform is higher than the energy to plastically deform. So the material just goes, whatever energy is first, I find plasticity, I'm going to transform. I'm going to deform. So it just goes plastically deforming, just like conventional steel. And this is the critical temperature, not the 500 degrees C. It's called the MD, the martensite desist. This is very critical in shape memory alloys. And when you see this pattern in superelasticity, but the takeaway from this message is most SMAs can show superelasticity above AF and martensite shape memory effect below MF. In other words, if I have a structure and it requires a superelastic alloy, I need to do something for that alloy so that AF is below what I needed to use. If I need to use this as an actuator, I need to operate between an MF and AF. So if I operate here, I have an actuator. If I operate here, I have a superelasticity. And it's really the same material. And here's why. Oh, that's ugly. Okay, let me clean up here. Okay, I don't know how to clean up, but okay. Erase. Okay, so here is why. And this goes into the material science part of things. If I take nickel and titanium that I mentioned before, and I do this atomic, if I add nickel or remove nickel, 50-50 is here, for example, 50% nickel, I take 5 grams of nickel and 5 grams of nickel, I mix them together, and that shape memory alloy gives me a transformation temperature MS, that stands for martensite starts, of say 340, whatever that is, Kelvin, for example. Okay, I'm here. But if let's say I need to change where the material is activated. I need to activate down here. What we do, we simply add nickel. We add nickel, more nickel. Now my MS is down here, 250. So what I mean is, if I need an actuator that needs to do some function in the cold place of the moon crater somewhere, that is -50 or -40 degrees C, my actuator can be designed with this amount of nickel. If I'm going to be on somewhere like in the hood of a car where it gets a little bit hot, it's not going to be cold, it's going to be hot, so I can design my alloy with 49% nickel or what have you, and create an alloy that transforms at higher temperature. So this is the game that we play in the alloy developments, and this is the simplest of them is nickel and titanium. Typically, we add a third element, a fourth element to tune this transformation temperature to a desired application. So if your application requires an activation at 200 degrees C, we can put some element here to move this line up and provide an alloy that can activate at those temperatures. That is the reason for having both elements.